Institute Colloquium. Today, we're very happy to have Juergen Jöst telling us about geometric principles of data visualization. So please, Juergen.
So thank you very much. Let me start with some general remarks or some assumptions. So the first assumption is that you all know a lot more about category theory than I do myself. The second assumption is that whenever a set occurs, it is usually a finite set. And whenever I speak about categories and whenever it makes sense, a category should be assumed to be small. And also, whenever you have any question or any doubts or criticism, please feel free to interrupt me. I'll be happy to try to answer any questions and respond to any criticism. And then about the organization of the talks, there will be an introduction, perhaps somewhat lengthy, then there will be a main part, and I will go through that main part. And then if time suffices, there's a couple of additional topics that I might like to address, but only if time suffices. Okay, so let's start with the introduction. So usually we are confronted with data sets, typically very large, and we want to analyze, interpret, and understand them. Now, all these data are often created by elaborate technical devices. You know that astronomical observations, particle collider experiments, imaging techniques in biology, and so on. And since they are outside our usual range of sensory experiences, they are difficult to analyze, to interpret, and to understand. And usually the scientists from these domains need some help. And so, therefore, human psychology, which guides us in our everyday life and helps us to interpret what we see, doesn't help us here. And so, therefore, of course, we are in business as mathematicians. But to do mathematics, we need structure. And of course, the structure comes from the fact that the data are typically not random. And so they should carry some structure, and we should exploit that structure. So how can we detect or get such a structure? Typically, the data come in some high-dimensional spaces, but intrinsically, they may be of much lower dimension because of correlations between data points, regularities, invariant symmetries, and that is what we need to exploit. And in particular, we then need to find good low-dimensional representations that bring out the essential features that are particular to the data at hand. And in fact, if you want to visualize them, you should even try to have representations in 2 or 3 dimensions, even though the data may naturally sit in much higher dimensions. So now, to become more concrete, we assume that the data come with a metric structure. That is, we have distances, perhaps some generalized distances between data points. There could simply be Euclidean distances when the data are presented in some Euclidean space. For example, when the axis records values of particular quantitative features, or there could be abstract inner distances and dissimilarities. And machine learning then extracts the features of the data from these metric relations. So that is the general program. And just give you some overview. I'm still in the introduction. One can do manifold learning. The data, as I said, might be given in some high-dimensional, typically Euclidean space, but they might lie or are concentrated near some low-dimensional smooth manifold, but this low-dimensional smooth manifold need not be linear, but it could stretch in many ambient directions, as you see in the example here of the saddle surface. And this manifold then should be recovered by sampling the data. You can also present the data as graphs. For example, you can connect data points that are sufficiently close or that are sufficiently similar, or that have a particular relation by an edge. And then use concepts from graph theory to identify particular features. Or more generally, we can use hypergraphs where more than two elements can entertain a relation. For example, in chemical reactions, where you have several educts that undergo reactions to produce several products. And we have topological data analysis, which will also come up in this talk. Technically, this is persistent homology. So for each radius r, one looks at the intersection pattern of the distance the data points x with radius r, and one turns these intersection patterns into a simplicial complex and computes its homology, its homology class, in particular its Betti numbers. And one identifies those homology classes that persist for a large range of radii as those that encode important morphological features of the data at the persistence scale. And in manifold learning, returning to that, we construct a graph by joining sufficiently close sample points. And when we have more and more samples, the eigenvalues and eigenfunctions of the corresponding graph Laplacian approximate those of the Laplace-Beltrami operator of the manifold and recover it. And network analysis can also use the eigenvalues and eigenfunctions of graphs and hypergraphs, but also curvature statistics as some foundations of machine learning and data analysis. And as I will try to explain, the intersection patterns of balls in topological data analysis can be related to curvature notions for metric spaces. So this is kind of the general setting. And here's an example. We have the skeleton of a mammoth. So the different body parts and protrusions are indicated in different colors. So this is a projection of a three-dimensional image, but we want to represent the thing, that skeleton truly in 2 dimensions. And here is one way of doing it. That is one machine learning algorithm. I will reveal which one it is later on, that somehow stretches out the different body protrusions, but not really in a perfect way. Here's another one. Again, that does that in a different way. And finally here, you see the results of the algorithm that I'm going to advertise in this lecture. You can clearly distinguish the different body protrusions by the machine learning algorithms that we are applying here. And so the aim, of course, is not to reproduce a stereographic projection, but to have a qualitative understanding of the image and of the different body parts and the different body protrusions. In particular, that is important when we look at truly high-dimensional images. So now, as I said, I want to present a method that we have developed with Lukas Barth, Hanane Fahimi, Pavane Yoharinat, and Janis Kek, and that builds upon and improves the popular UMAP method, which probably you have heard about, because in particular, some of the work of David Spivak here is underlying that method, and so we can also build upon that. So as I said, data are often given in some high-dimensional Euclidean space. They carry distances, and they possess intrinsic regularities and correlations. That is intrinsically they are lower dimensional. And so they may even sit on a smooth lower dimensional manifold. And to have a manifold is good if you want to interpolate between data points. But this manifold need not be linear, and it may be highly curved, and may stretch into many ambient directions, and you may still want to capture it. And also, one technical problem is that the data need not be uniformly distributed on that manifold, and that will be a particular aspect of our method that we are capable to deal with that. And we want to ultimately visualize the data in 2 or 3 dimensions while preserving the qualitative aspects, in particular the clusters in the data as well as possible. There are some existing methods, IsUMap, TSNE, and UMAP that I've mentioned already. And the general idea, of course, is simple. You have the data points. That is all what you have. You just have a sample, and you connect those data points that are sufficiently close to get a graph. And when more and more data points are sampled, the graph gets denser and denser and should ultimately approximate a manifold in a sense that needs to be made mathematically precise. And in particular, we want to represent these graphs in the end in 2 dimensions in such a way that we are able to see or to highlight the essential features of the data manifold. But of course, not everything that is in high dimensions is apparent if we map it into 2 dimensions. And so aspects get lost, and we want to lose as little of the qualitative aspects as possible. So therefore, we cannot just take the graph as it is, but we need to pre-process and modify it in order to amplify local features, in particular clusters, before projecting. That is a basic idea of the methods. So, of course, as I said, you construct a graph, so you connect each data point with its k-nearest neighbors to get a collection of star graphs. So each star has a center, and the peripheral vertices are the k-nearest neighbors of that center. Simple. Now we have these different star graphs, and we want to merge them. Of course, they're already merged, but the point is we want to merge them in such a way that we can better see the global structure analyzing them and underlying them. And then we want to project the resulting space into 2 dimensions with minimal distortion. These are standard schemes on which I will not spend that much time. So, but let's look at the inspiration. So, the person who inspired the prize was Bernard Riemann, who was born almost 200 years ago. And in 1854, introduced the abstract concept of a manifold of arbitrary dimension n, equipped with a metric tensor Gij, with which one can compute a scalar product between tangent vectors at a point. So, but this is represented in local coordinates. And in other coordinates, the tangent vectors and the metric tensor look different, but the important point is they transform in such a way that the scalar quantity that I've mentioned remains the same. And in fact, this is a principle of covariance that is fundamental for Einstein's theory of general relativity, and it tells us that we should look for intrinsic properties that do not depend on the representation, on the coordinate representation. And therefore, you want to find invariance. And Riemann posed and solved the problem of determining a complete set of local invariants for such a metric tensor. And they come from the curvature tensor that he introduced. And they come essentially from second derivatives of a metric from a formula that looks a little complicated, and we will not need the precise formula. But for the moment, we do not need the curvatures. We only need the concept of Riemannian metric. But Riemann introduced another important device, that of normal coordinates. And that means the following. You take a point in a Riemannian manifold, and you look at the vicinity of the point. And for other points that are in the vicinity of P, you record the distance from the center P and the angles that the shortest geodesic between, for going to different Qs, make with each other or with some reference direction at P. That's the principle of Euclidean polar coordinates transferred to Riemannian geometry. And importantly, these coordinates then exhibit what the manifold locally looks like from the perspective of the center P. And that is a crucial idea in what is following, even though that may look very simple. And of course, this does not work globally, because in general, the shortest geodesic from P to more distant points in M need not be unique. So you can do that only in the vicinity of a point. So now we have a discrete metric space, and so we imitate that. So we take a point X, we take its k nearest neighbors x1 up to xk, ranked according to the distance from P. So x1 is that neighbor that is closest to P, and xk is thus that neighbor that has the k's largest distance from P. And then we consider the star graph with x as its central vertex, and thus edges of length equal to the distance from x to the corresponding peripheral vertex xj. Very simple construction. So that is our starting, but these are our starting points. But for computational reasons, now we will modify the metric. So now it becomes a little more complicated, but we can go through the formula. So dx, xj is the original distance. So we subtract some number from it, and we normalize it by a factor sigma x. And we also now introduce distance between two different neighbors. I put the factor 1 over square root of 2 here, but you could also take another factor. And for every other point, for any other points that are not either x or among the k nearest neighbors of x, we simply put the distance equal to infinity. Yeah, so we just ignore all the other points that are not in the vicinity. That is what this metric is doing. So in UMAP, the scheme that I alluded to, you even put the distance equal to infinity between different neighbors of the center x. So we don't have the third line with the factor 1 over square root of 2. Instead, in UMAP, you just have infinity. But then, of course, you violate the triangle inequality, as you easily check. And I want to preserve the triangle inequality here. So factor 1 over square root of 2 simply mimics the Euclidean distance of the ends of orthogonal vertices, and one could omit it, just put 1 there, or replace it even if you want to by different factor. And I will now explain the choice of the subtractive constant rho x and of the normalizing factor sigma x. But first of all, let's introduce the category, namely that of ubermetric spaces, introduced by David. And in fact, at some point, David should tell me why he chose the name ubermetric here. But perhaps we can do that at the end. Anyway, an ubermetric space is a set equipped with a map that satisfies all the properties of a metric, except that it may take the value infinity. But it still has to satisfy the triangle inequality. So if the distance between two vertices is equal to infinity, then for any other vertex, also the distance to at least one of them needs to be infinite. And so this is a basic category that we shall work with. And typically, we just work with a category of finite ubermetric spaces, although I will not always say that explicitly. And so now, what about rho x and sigma x? So for rho x, we just subtract the distance from the closest nearest neighbor. And so then that distance becomes 0. In fact, that is another aspect of metric spaces. Distances also between different points could in principle be 0. So why am I doing that? Well, I do that in order to ease the curse of dimensionality, because randomly picked points in a high-dimensional ball tend to cluster around near the outer boundary. And so I want to make the distances to the neighbors more uniform by subtracting that one. But that again, that is not really necessary. And sigma x, that is a normalization factor to handle the fact that the distances between the points need not be uniformly distributed. There could be denser and sparser regions, and somehow I want to treat all of them at the same scale. That is why I normalize by the distance to the largest among the k nearest neighbors. So now, for the closest neighbor is already set as distance 0, and the largest neighbor is distance less than 1. And you have the triangle inequality, and all the vertices that are not in the star have infinite distance and therefore are not seen from the center. So that is a rather drastic application of Riemann's locality principle or localization principle. Now, we have these star graphs, and they have different metrics, and the metrics need no longer be compatible with each other because of the normalizations that depend on the center and its neighborhood. And of course, we want to recombine them into a global structure, and so that is the main part. So we have two options, or at least I see two options. We could simply develop a canonical scheme for merging metric spaces, or one could convert them into fuzzy graphs that can be merged in a canonical way with the help of what is called a T conorm and utilizing constructions from category theory. And as you know, fuzzy graphs are a special case of Spivak's fuzzy simplicial sets, and these ideas will again show up below. Now, here I will develop the first alternative, but you, as being experts there, will clearly see the analogy with Spivak's fuzzy simplicial sets, even though I will not point that out at every stage explicitly. But I should also point out that an essential idea already goes back much earlier, namely to Carl Menger, the geometer or topologist Carl Menger, who published this in 1942. And so I will not define fuzzy sets, I will define here hazy sets. But as I said, you will see the analogy clearly. So we take the closed interval from 0 to infinity, the open sets for that topology are thus the intervals from S to infinity, including infinity, but not S. And such an interval I will often simply indicate by S, and then we have the inclusion. So when t is larger than S, of course, the interval from t to infinity is smaller, so it's included into the interval from S to infinity, and so that gives us a category called H for hazy. Now, then a hazy set then simply is a sheaf on H for which all restriction maps, they now go into the opposite direction because we are dealing with a sheaf, for which all these restriction maps are injections. And so that category is denoted by Haze. And we simply call S the haziness of such a set SS, and consider SS as a set of haziness at most S. So the idea is the smaller the haziness, the more certain we are that the point is actually there. Haziness equal to 0 somehow means that the point is certainly there, and haziness infinity means that the point is certainly absent, and with haziness values in between, we cannot really tell. And of course, we can take S infinity, that is the largest set, and then all of them are all the others are subsets of S, and we can of course also take the sets of haziness precisely T if we want to, but that will not be so important here. So now we also need hazy simplicial sets, again analogous to the fuzzy simplicial sets as functors from the opposite of the simplicial index category to our category Haze. And then we have the functor category S Haze of hazy simplicial sets. And so hazy simplicial set simply is a functor from the opposite category of the indexing set cross H to sets. And then we have S and S, the n simplices in the image of S of haziness at most S. And now it's an important point, a simplex is at least as hazy as its faces. So in other words, if it's there with a certain haziness or degree of probability, all its faces are there with at least the same, if not a higher degree of probability. Particular vertices are always there, that is what we usually assume. The edges are there with a certain haziness, triangles with possibly even higher haziness and so on, until things disappear at infinity. So now when we use the Loneda embedding of embedding our category into a presheaf category, then we obtain corresponding functors. And thus by the properties of our topology, they only exist, these morphisms, they exist only for S less or equal to T. And so far, we also get morphisms from delta NS to delta LR only if R is less or equal to S. And so we consider delta NS as a n simplices of haziness at most S. And as you all know, this is thus the convenient way of translating the geometric properties into abstract ones that we can handle with the formal tools of category theory. And so now we have a couple of functors. Now we have a functor that we have called smear functor. I don't know whether you like the name. Perhaps I should choose a different one. When we have such a hazy simplex, then we look at the geometric simplex. And the geometric simplex is operating at a scale S. That is the important point in N, that we have all points in Rn plus 1 with non-negative coordinates such that the sum of the coordinates is equal to S. And so when we have morphisms, then we can simply rescale things by factor S over T to go from a simplex with size S to a simplex with size T. But S needs to be less or equal than T in order to have morphisms that are distance non-increasing, as we always require when we look at metric spaces or categories of metric or spaces or generalized metric spaces. So this is kind of a geometric realization. No, but we can use Kahn extensions. Of course, the principle is simply while a functor between small categories need not admit adjoints, it lifts to the Yoneda categories of pre-sheaf stars, and we make full use of that to extend this to a functor from the simplicial Hazy sets to Uber metric spaces. So first we had the functor that associates to each simplex, to each Hazy simplex, a geometric simplex, but then when we have simplicial Hazy sets, that is simplices glued along their boundaries, then we get a functor to an Uber-metric space. So the important point is that the image of a Hazy simplicial set is Uber-metric. So simplices have a metric given by formula 9 that is compatible with gluing along shared faces. And as I explained, the faces cannot be more hazy than the simplex itself. And so hence, the diameter of a face cannot be larger as the diameter of a simplex that is in whose boundary it is. And in particular, if you have a shortest path traveling inside the face, we cannot make it shorter by going into some ambient higher dimensional simplex. But we also want to go in the opposite direction. We want to go from Uber-metric space to a simplicial Hazy set. So therefore we introduce another functor, which I've called the tightening functor. Again, a name that you may not like, and I'm open to change the name. So now we have a Uber-metric space, and so we need to go from every element of the opposite category of delta cross H, and assign to it a set. And of course, we assign to it the morphisms of the smeared simplex, the geometric realization of the simplex into the corresponding Uber-metric space. And importantly, again, morphisms in category of Uber-metric spaces are distance non-increasing, and therefore the larger S is, the more morphisms we can have into a given Uber-metric space. Because when S is larger, the corresponding geometric simplex becomes correspondingly larger, and we have more possibilities to map it into an Uber-metric space without increasing distances. And then one proves, or we could prove, that the tightening functor is a right adjoint of the smearing functor. And so that, of course, will then allow us to go back and forth between the two categories. So now, since we have the category theory at our disposal, now we return to the geometry, and we need a merger tool in order to carry out the task that are indicated in the beginning, namely to merge our star graphs. So we define an M scheme as a functor, as a function from 0 infinity, the range of the Uber distances across 0 infinity to 0 infinity that satisfy a couple of properties. It needs to be symmetric. It needs to be monotonic. That is, when we merge smaller distances, then also the result should be smaller than if we merge larger distances, and it should be associative so that we can merge several Uber-metric spaces or whatever we want in a manner that does not depend on the order. And so we also need to have some boundary condition. If one of the distances is infinite and the other is S, then the merged distance should also be S. So here's an exercise, and I gave you the solution of the exercise already. Any M scheme satisfies M of S, 0 is equal to m of 0, s by monotonicity, and that is 0 for all s. Well, this follows from the boundary condition 4, since m of 0 infinity is equal to 0, and then you simply apply monotonicity, and I've already applied symmetry in the argument. I should say that should make some remarks here. They are not on the slides, but first of all, these M schemes have appeared in the literature before. They've been called composition laws, and of course, the analogs of the T conorms, and this analogy was already pointed out by Karl Menger in the works that are indicated and the subsequent paper of his. But let's return to these M schemes. So we have two extremal examples. First of all, we have the minimum M scheme, where min means minimum and not minimal. That is important here. Where for S and T, you just take the minimum of S and T. There's another extreme one. You put everything to 0, except if one of the arguments is equal to infinity, then you let it just be equal to the other argument. And of course, you see that M min is larger equal than mx all the time. Yeah, so min is not minimal. Yeah, now we want to embed them into some family. So we take a subset of the non-negative real numbers, and then instead of mx, again we put the result of the merger equal to s or t if the other argument is infinity, and otherwise we put it equal to the supremum of all v in our set v that are less or equal to s and less or equal to t. If we take v as the entire positive reals, then again we get our minimum M scheme. If we take v just equal to 0, the set containing 0, v should always contain 0, then we get mx, the other extremal one. But for example, we could also take v just equal to the positive integers if we want to. But in any case, if u is a subset of v, then m of u is less or equal than m of v, because simply we are taking the supremum then over a larger set. And then we just let v to be equal to the interval from 0 to a, we get a natural family that interpolates between the two extremal examples m min and mx. So now we can use that for merging. A Hazy simplicial set derived from a Uber-metric space is a diagram or inverse system of simplicial sets. I will not really go into all that category theoretical terminology here, but we construct a classical Hazy simplicial set, whatever that is, or it's just implicitly defined here, which consists of a simplicial set. N-dimensional simplices are identified along common boundaries, along with a haziness function. And this Hazy simplicial set is then realized as a metric space through a smearing process. So that is important part.
Juergen, can I?
Yeah.
Sorry,
Sure.
can I interrupt, Juergen? Were you saying, what do you mean that the n-dimensional simplices are identified? You don't mean made equal, you mean something else?
Yeah, no, then I mean, that's in the way that one has a simplicial complex where simplices are glued along common faces.
Mm-hmm. So the n-dimensional simplices for some size n are
sure.
marked.
Sure. So I mean, I don't want to make this precise.
Okay.
Just take of a simplicial complex. They have a couple of simplices that are glued together along shared faces. And just think of that within the categories that we are dealing with here.
Okay, thanks.
So now we come back to our situation. We have a finite vertex set. That's our data sample on which we then build a Hazy simplicial set. And so the important properties that we need is that the haziness of a simplex is at least equal to the haziness of all its faces. The vertices have haziness 0, and when the scale of the haziness, our S that I had before, is larger or equal to the diameter, that entire space is thus represented as a full simplex equipped with a haziness function. Then we just have a full simplex on our vertex set. And all its faces also have certain degrees of haziness. And now we went in one direction from a Uber-metric space to a Hazy simplicial set, and then the triangle inequality is implicitly reflected in the haziness of edges. But we need to be careful, because in general, the edges of a Hazy simplicial set need not satisfy a triangle inequality. Yeah, just think of a triangle that has 3 edges, and the edges have certain lengths or haziness or whatever, but within the framework I'm having here, they need not satisfy the triangle inequality. But the important point is, in the backward direction, when we go from a Hazy simplicial set to an Uber-metric, as a functor that I have described, this ensures all the Uber-metric properties, including the triangle inequality, because we are looking at all these morphisms into Uber-metric spaces. So here's just an example of why the triangle inequality is not satisfied. Let's take 3 metrics. In the first one, the points y and z. The point y has distance 1 from x, but the 2 other distances are equal to 3. In the second example, the point z has distance 1 from x, but the 2 other distances again are equal to 3. And when we just take the minimum merger function, then the distance between x and y becomes 1, because that is the minimum of the 2 distances, delta 1 and delta 2 between x and y. The distance between x and z becomes 1, again, because it's the minimum of the 2 distances in delta 1 and delta 2. But the distance between y and z is equal to 3, because that is just the same value in both of them. And then we no longer have the triangle inequality. The distance between y and z is 3, but if we go from y to x, and from x to z, then we only have to travel a distance of 2.
Are these distances or hazinesses? Sorry to interrupt again.
Well,
Are these
at the moment, I'm
distances?
talking about real distance. Yeah.
Okay,
Yeah,
okay.
but, I mean, we can try to switch whenever we want with the tools that I have here, but at the moment, these are just ordinary distances. Just have a simple ordinary metric space here. And so we have, in our more precise, we have 2 metric spaces that we want to merge. But if we do it naively, then we don't have the triangle we need not preserve the triangle inequality, even though individually both of them did. That is just the point of this example here.
Got it. Thank you.
And so, therefore, we need to do something different. We just need to define the distance as some infimum of paths going in the two different metric spaces from one to each other. So whenever we get a shorter distance in one than in the other, we switch where we are going. So now again back to our star graphs. We had constructed the star graphs centered at the sample point X, and each sample point was connected with its k nearest neighbors. But now we have modified the metrics by subtracting a quantity and by scaling with a quantity that depended on the corresponding center. And so if X and Y now are both among the k nearest neighbors of each other, that of course can actually happen, the weights of the edges in the corresponding star graphs in general will be different. And other weights are even infinite. And so we then use the above scheme to merge these star graphs to reconstruct some graph that represents the entire sample.
All right, Juergen, sorry to interrupt again, but you asked me to interrupt between 45 and 50. So I'm just letting you know.
Okay, good. Yeah, I'll try to come to the end quickly then. Yeah. So of course, why didn't we just simply construct a graph from the sample by connecting sufficiently close points and use the ordinal distances, or connect 2 points when at least one of them is the k nearest neighbors of the other? In fact, an early scheme did that, but in fact, things can be improved considerably by using that intermediate procedure that we have and go through all the category theoretical complications. So here again is then our merging scheme, where we can just use the star graph in every step where the distance is smallest. And that is just for that particular formula 14 just comes up when we use a minimum merging scheme. We can experiment with other merging schemes, and we have done that. But now the procedure of the scheme is we construct star graphs with the UMAP metrics as I have described, adjust and normalize these metrics, then merge the local star graphs as I have described in some detail. Then one uses a classical algorithm from the 1950s to compute the distance function on the resulting global graph. And then one uses some standard scheme like multidimensional scaling in order to approximate it by a two-dimensional graph by keeping the distances as close as possible. So here are some results. So the upper left, A, is the original data set. So it's just a hemisphere, but with points distributed on it with varying density. B is the result of our method. C is the IsUMap method, which didn't do this intermediate renormalization of the star graphs. And D is the UMAP method, which did the normalization of star graphs differently, and also the merging and the projecting differently. And so again, here we have the examples that I showed in the beginning: the mammoth skeleton, our method, IsUMap, and UMAP in comparison. Here are some other examples, standard examples, Swiss roll and the Toro. Again, in the second column, you see our method, and in the right column, you see others. In the third and fourth column, you see others.
Sorry to interrupt.
Some biological.
It didn't scale. Sorry, Juergen.
Please.
It didn't move on people's screen for a while. Now we see it. Can you say this one again?
Yeah. Okay. So, did you see the mammoth data set?
Yeah, we saw that one, but this one paused. So this one would be good to see.
Okay. Yeah. So we have the Swiss roll and the Taurus, left column. Then we apply our method to represent it. And then you see two of the other methods, IsUMap again, which somehow looks smoother or nicer than our method for this particular example. And then you see UMAP, which somehow stretches or distorts things more. So UMAP has somehow the property to emphasize clusters even more at the expense of between them. There are some biological data sets, but for lack of time, I will not go through them. Maybe just in the end, I indicated that we can, or I showed how to construct a Hazy simplicial complex from a metric data set. And so you know what a simplicial complex is. And in a Hazy simplicial complex, all simplices carry haziness values. All the faces have a haziness value not larger than that of the simplex itself. And now, somehow the haziness simply is kind of a different way of talking about the radius that one uses in topological data analysis. And the section of distance balls, and we just interpret it as a haziness value. But I don't know whether I have a few more minutes or whether I should stop here for questions.
Maybe we should stop, and then somebody's question could be, tell us about topology and curvature.
Okay, good. Yeah. Then I just go to the list of references that we can have that. Yeah. So as you see, I could have talked a lot more, but here are the main references. And so the last one is not even fully visible, but that again is an archive paper that we just posted a couple of weeks ago.
Wonderful.
So I'm happy to receive questions now.
Okay, well, thanks for your talk. So everyone, if you have a question, you can raise your hand using the react button. I see one already. Yeah, Marzia, maybe you could unmute yourself.
Hello. Hello, Juergen, and thanks a lot for the very nice seminar, and thanks to Professor Spivak also. I have a question about the very main assumption that you have for this whole structure, the manifold hypothesis. Do you think, is it possible to extend this categorical approach to the case that we don't have that assumption in our data, like when we have stratified spaces or singularities? I mean, I understand that you are basically sampling data points uniformly, and it is much less likely to sample points in the stratified parts. But I mean, do you think there is any obstacle for extending the categorical parts? I mean, having some star graphs that are coming from that stratified cases too? Thank you.
Yeah, sure. Of course, that is a very good question. Thank you, Marzia. Now, the point is, I didn't really use the manifold hypothesis here. Yeah. So the scheme that I've presented here is general enough to also capture non-manifold data. And of course, even some of the examples that are presented were either non-manifolds or manifolds with holes or boundaries and so on. But nevertheless, in general, in machine learning, the manifold hypothesis is quite important, because if you have a manifold and you have a couple of points and a local vicinity, then you roughly know what the structure looks like between the points. It may deviate a little locally, but essentially it is smoothly interpolating between the data points. Yeah, and so therefore, even if you have just a finite sample, you roughly know what the underlying structure is, whether it really exists or whether it's just a putative structure. You can nicely interpolate. That you can no longer do if you have singularities. If you sample from a space with singularities, then if you take random samples, singularities are lower dimensional, so they have measure 0, and then you will not capture the singularity.
Sure.
Yeah, but of course now in topological data analysis, there are schemes to handle that. Instead of looking at the distance ball, you look at annuli, and you look at the geometry of annuli. Yeah. So for example, if you have if you have two planes intersecting at a non-zero angle, take a point in the intersection and look at its neighborhood. Then if you just look at the neighborhood ball, it's contractible, so you don't see anything. But if you look at an annulus, the difference of two balls, then you see some structure. Then for these two intersecting planes, you see four different handles, and so that gives you some topology already, some first Betti number. Yeah, and in fact, no, it would be a natural next step to include these things into the manifold learning schemes and explore what you can actually do also with this notion of generalized curvature and so on. But you're pointing right towards one of the most natural and immediate research questions that we would have now.
Sorry, if you can I just have probably a follow-up question to one of the things that you mentioned, like for the TDA and usage of this simplicial Hazy complexes, what you would expect to receive more? I mean, what would be the intuition of homology groups there when you have this? Because you shouldn't have, of course, from one simplex to another, you don't have a stable radius. Of course, the radius are changing based on the intersections of two simplicial complexes, I think, in your setting, which is not the case in TDA. So how would be the intuition for, I don't know, the main things that we are following in TDA or we are looking for in TDA, like the homology groups when we change the radius?
Yeah, well, that is a good question, though probably one needs to go to a larger category than the simplicial category here to capture these more refined topological aspects. But
what would be even the intuition for you for topological aspect? When you have when you don't have a fixed radius, basically? I mean, it is of course not a radius, but this number that is changing from the faces to another faces of the next simplicial complex next to it.
Yeah, I mean, at every stage, one should look at two radii and look at the difference of the balls and the intersection patterns for the difference of the balls. Yeah.
Okay. Well, thank you for your question, Marzieh. And we can stay after a bit on the Zoom also if there are follow-ups.
Thank you so much sorry for the a bit long, but yeah, I was just having these questions. Thank you.
That's very nice.
It was a very, very good question.
Yeah, and again, we can stay on after the live stream ends. I had a quick question, Juergen. How does UMAP compare with TSNE or UMAP? Sorry, how does IsUMap compare with, say, UMAP or TSNE or some of the others in terms of the time it takes to run or the complexity of setting it up on a computer? Is it more difficult, or?
It takes a little longer, but not because of the main steps that I described, but since we apply the Dijkstra algorithm and the multidimensional scaling also, so UMAP has some shortcuts there. Yeah, and so UMAP.
These are shortcuts that you. These are shortcuts that you could also employ if you had more people working on it, or no? It's just going to always be slower for some reason.
No, I think we could apply them, but then some of the advantages of our method actually may get lost.
I see. I
mean, we claim that we have better results on a couple of data sets that come from a combination of the theoretical scheme that we use, namely that we put the Uber matrix that we put metrics instead of extended pseudometrics on our star graphs, and also because for projecting into two dimensions, we use somewhat more expensive schemes.
Mm-hmm. Cool. Well, I think if there are no more questions, we'll end the live stream here. Thanks again, Juergen. And we'll end the recording. And then, let's see, where's that stop recording button? There it is.